In this second part of chapter 5, we will deal with life and ecosystem. And I hope I will convince you that in order to understand ecosystem and life on Earth, it's impossible to do so without understanding basic redox chemistry. Because life is nothing else than redox processes. Why? Just going back to what an organism needs to live. What do we need as human beings to live? We know that life is carbon-based. We need a lot of other components, of course. You need nutrients, you need a lot of elements in the periodic table to live. But the main component that is providing the large molecules that allow you to do enzyme, to do lipids, to do all the elements needed in a body, is based on the fact that you can build long chain of carbon, long organic carbon molecules, complex one, that allow you to do complex machinery. So this is why you have carbon-based life, because carbon has this oxidation number, about 4, and can do bonding with other carbon and other elements and very complex molecules. So carbon is very important. So life needs what we call a source of carbon to do cells, to produce tissue. But also what you need is a source of energy. And this is very important because it's not only good to do cells and organic matter, but you need to do work. In the cell, you need to perform chemical reaction to give you what we call ATP. We'll see that, this adenosine triphosphate, this molecule that is storing this universal unit for storing energy in any organism on Earth. So to do that, you need energy to create this ATP, to store energy in this ATP. That will then be broken down to ADP, adenosine diphosphate, just by breaking one phosphate group. That this breaking the bond will allow you to do work. So both of those are called metabolism. Metabolism is nothing else than, for an organism, trying to find a way to get a source of carbon and a source of energy. If you want to go into more detail, the carbon source, carbon, is called the anabolism, and the energy part is called the catabolism. And those two together are what we call the metabolism. So, source of energy can be seen as creating a current, a potential between two substances, and by using the potential, the electrical potential in between two substances, you are able to create a current, and this current can be then transformed into energy, like in the battery, nothing else than a battery. So life in every cell is doing battery. In our case, in the case of most eukaryotes, the eukaryotes are the organisms with cell with nucleus, we are eukaryotes, are doing as a metabolism what we call respiration. And to be more precise, aerobic respiration. So what we are doing as organism, we are taking a source of carbon, which is, for example, I'm going to simplify that by creating CH2O, but you can write, for example, say 6H12O6, which is glucose, and then you're going to put this glucose in relation with oxygen, and you will create CO2 plus H2O. This is aerobic respiration. What you're going to do is use this reduced form of carbon, we have seen that just before, to produce an oxidized form of carbon, And this is an oxidized form of oxygen, and this is a reduced form of oxygen. So this equation here, this reaction here, has a delta G0 that is negative. It's around, I think it's minus 448 kilojoule per mole. So it's a spontaneous process. As soon as you pushing a little bit with some activation energy, this can go on and on and on and release here energy. Okay, so what is it is just nothing else than a redox reaction. The organic matter, symbolized by this CH2O, the organic matter, is going to be oxidized into CO2, and the oxygen is going to be reduced into water. If you remember, the oxidation state of water here is 0. Let's put that in another color. And the oxidation state of oxygen in H2O is -2. So this is definitely a reduction. You're reducing this number here. You're adding electron. In this case, this oxidation state is 0, and this oxidation state here in this case is +4. You have clearly an oxidation. And this is the first part of the carbon cycling, the respiration. So if I'm writing a very simplified carbon cycling here, when you have the organic carbon here, the more reduced, or a reduced form of carbon, whatever, it's organic carbon, that will be then oxidized in CO2. And this is what we call respiration. In this case, is aerobic respiration because it's using oxygen. So what I want you to think is the organic matter is full of electrons. The organic carbon is a reduced form of carbon, meaning he has a lot of electrons. And those electrons can be a source for a current, for a battery. And a process is that will be able to rip those electrons away and to give it to something else. In the process, creating energy will be very favorable. In our case, the electrons that are on the organic matter will be then absorbed by another color in green, will be absorbed by oxygen that will be taking this electron and form H2O. Okay? So you have a coupling between the carbon cycling, which is oxidation of organic carbon into CO2, with the reduction of O2 into water. And this is very important. This is a redox equation. So this organic carbon is a pile of electrons, and that can be then used for energy. So you need an electron acceptor. So again, I'm going to write that down because it's important. In energy formation, in a metabolism, you need an electron donor, and you need an electron acceptor, because electrons cannot stay like that naked in environments. In the case of respiration, the electron donor is organic carbon, electron acceptor is oxygen. So that's the first half carbon cycling, very simplified carbon cycling. I'm sure you know that, and we've already seen that the second arm of this carbon cycling is, I'm going to put that in green, now let's put that in dark green, is, oh, that's too dark, is the opposite reaction that is going to do, is going to take CO2 plus H2O, that will give you organic matter plus oxygen. And you now know that this is photosynthesis. So photosynthesis is nothing else than the reversed reaction or reversed metabolism as aerobic respiration. Or we can see the opposite way. Aerobic respiration is a reverse process of photosynthesis. What we have is CO2, that is an oxidized form of carbon, will be reduced into CH2O, and the H2O will be oxidized into molecular oxygen, gaseous oxygen. For photosynthesis, the electron donor is what? Is H2O, and the electron acceptor, in this case, is CO2. Photosynthesis is nothing else than a redox equation, a fixation of CO2. So photosynthesis is CO2 fixation. To do that, you need energy and a reducing power, a reducing agent, because CO2 is oxidized and you need electron to reduce this CO2 into organic carbon. And those electrons are coming from the dissociation of the water. But those electrons, they don't have enough energy to oxidize the CO2. You need a strong reducing power to reduce CO2. It's not easy to do that. You need a lot of energy. Because if you write the delta G of this equation here, delta G0 of this equation is positive. It's plus 448 kilojoule per mole, the opposite as the respiration. So you need energy in order to go forward with this reaction. And where this energy is coming from is from the sun. So the sun is providing photon. Now you know, you have photon with different energy. So they're producing high energy photon that will be absorbed by electron. Those electrons are coming from the dissociation of water. Those electrons will be then absorbing those photons, getting a lot more energy, and this will be used to then reduce the CO2. This is a simplification way. I can go more into detail about the photosynthetic activity and the two photosystems, but it might be a little bit too much detail for this course. That might be for a more advanced course. But just for this part of the course here, I want you to think about the fact that CO2 is reduced to organic matter. And for doing that, you need energy from the sun. The sun will give you high energy electron because they're producing photon that will excite those electrons that will be able to reduce the CO2. So photosynthesis is a fixation of CO2 into organic matter. Photosynthesis is nothing else than a redox equation that is piling solar energy into organic matter. So you have the sun, you have the CO2, the interaction with that through photosynthesis will store that in organic carbon. And this organic carbon is loaded with high energy electron that can be used for respiration. So originally, of course, you understand that to create massive amount of organic carbon that we can consume, you need primary production, you need photosynthesis. So photosynthesis in some way has to be first, or has to come really first, if you want to have a strong, a robust functioning ecosystem. So here we have a very simplified carbon cycling. Okay. Again, in summary, CO2 from the atmosphere that is dissolved into water can be fixed through photosynthesis here. This process needs energy. Delta G0 is positive. So this energy is coming from the sun, providing the photon, able to reduce the CO2 into organic carbon. Then this organic carbon can be used by other organisms that's doing aerobic respiration, so using those electrons, those bank of electrons, stored into the organic carbon to produce energy and produce CO2 and water back. So that's a basic carbon cycling.